In a previous video, we discussed how a magnet produces an influence around itself, making its presence felt far away from it. We call this the magnetic field. And when other magnets come in contact with this magnetic field, they automatically experience a force. So it's the magnetic fields that push and pull other magnets. But guess what? Imagining magnetic field like this green cloud isn't going to be very useful for us, because it doesn't tell us anything about where the force is strong and where it is weak. For example, we know that the force is very strong close to the magnet, but it gets weaker as it goes farther away. It also doesn't tell us in what direction other magnets would experience a force. It's for these reasons today we have a better way of imagining this magnetic field. We do that by drawing lines everywhere. We call them the magnetic field lines. And so in this video, we'll see exactly how to draw these magnetic field lines and how do we read them. So to start drawing magnetic field lines, the first thing we need to do is define a direction for this magnetic field. And we decided that the direction of the magnetic field at any point is going to be the direction in which the north pole of a magnet would experience a force. For example, if I want to know what's the direction of the magnetic field here, then I have to keep a tiny magnet at this point and check what direction the north pole of that magnet would experience a force. And we can do that by introducing a compass. Because a compass has a tiny magnet which is free to rotate, so it will show me what direction the force is. And the red of the compass is the north, the black of the compass is the south. So I'm going to keep my compass over here. And notice the north is being attracted by the south, and as a result the north is being pulled this way. And therefore, by definition, the magnetic field at this point is in this direction. Similarly, if I want it over here, I'm going to keep my compass again at that point. And now we see that the north pole is being pushed away, repelled by this north pole in this direction. And therefore, the magnetic field over here is this way. These 2 points were easy to predict because over here the north pole gets attracted and here the north pole gets repelled. But what if I take some arbitrary point, somewhere over here or somewhere over here, let's say? Then it's not so easy to predict, but experimentally I just have to keep my compass over there and see what direction the needle points. Now notice the north pole points in this direction. And so the magnetic field is this way. And you may be wondering, why do we choose north pole? Why not the south pole? Well, people decided, well, we have to choose one of them as a standard. And so we just decided we'll take north pole as a standard. That's all. There's no other reason for this. And now if I want to draw the magnetic field direction everywhere, I have to keep repeating this experiment. Just keep moving my compass at different locations and keep drawing the arrow marks. That's fun, but that's a little tedious to do over here. So guess what? There's a simulation on Khan Academy where you can perform the same experiment but over the software. So it's going to become much faster. So let's go to that simulation and let's perform this experiment and figure out what the magnetic field direction is everywhere. So here we are. This is the code of this program, which we don't have to worry about. And this is the simulation where we start playing. Now, before we start, I have put the link of this simulation in the description. So if maybe after the video, if you want to come over here and start playing with it, just click on that. All right, so here's the setup is pretty much similar. We have a bar magnet and we have a compass, which will help us find the direction of the magnetic field. And it says over here, press spacebar to draw an arrow. That's what I like about this. So for example, over here, we know now the direction of the magnetic field is the north pole, so it's towards the left. If I press spacebar, automatically an arrow comes over there. Again, I press spacebar, an arrow comes over here. Press spacebar, arrow comes over there. So what we'll do is we'll press spacebar everywhere. We'll find out what the magnetic field looks like everywhere. So let's do this. It's gonna look initially all random, but as we draw more and more arrow marks, hopefully a pattern will emerge. And we'll speed it up so that we'll not waste too much time. So let's paste this picture back to our drawing board. Now, if you look at this picture carefully, can you see an interesting pattern developed over here? Look at all the arrow marks. They're all pointing away from the north, and they're slowly turning and pointing towards the south. And so the way we represent magnetic field today is we draw continuous lines, not arrow marks, but continuous lines that start from the north and move towards the south. We draw lines because it's easier to draw them compared to arrow marks. It's very tedious to draw arrow marks everywhere. So we would draw lines like this, and we put an arrow mark representing north to south. This is how we represent magnetic fields today, from north to south, everywhere from north to south. Now I know this is a little bit shabby, so I've already drawn a better version of this. So here it is. Now let's list down some of important properties of this magnetic field lines. The first property is that the lines start from the north and end into the south. But this is outside the bar magnet. If we were to peek inside the magnet, then you see that the lines run from south to north, closing the entire loop. And so, in short, we see that outside, the magnetic field lines run from north to south. Inside, they run from south to north. And as a result, we will always see that the magnetic field lines are always closed loops. Even this loop is a completely closed loop, all of them. Now you may be wondering, why is it inside south to north? How does that work? And the way I like to think about this is, let's say I break open this magnet to figure out what direction the field is inside. Well, then all I have to do is bring my compass in between and see what direction the North Pole points. Now you might expect that if I bring my compass over here and keep it over here, the North Pole will point this way, towards the south of that, and as a result the magnetic field line must be from north to south like this. But if you keep the compass in between, notice that the red needle, the North Pole, is pointing in this direction, meaning the magnetic field is from south to north inside the magnet. But why is that? Well, that's because when I broke open this magnet, I did not get a south pole and a north pole, but I got two magnets, two tiny magnets, each having its own north and south, and similarly north and south. And just like always, this needle is being repelled by this new North Pole and being attracted by this new South Pole. And as a result, the magnetic field inside is from the original south to the original north. Another important property of the field lines is that wherever the lines are closer, it means we have more field strength. So if you look at the field, notice that close to the poles, the lines are very close, which means the field is very strong over here. And as you go farther away from the poles, notice the lines go farther away, which means the field is pretty weak over here. And this can be seen experimentally as well. If you sprinkle some iron filings on a bar magnet, you see a huge crowd of them close to the poles of the magnet, revealing us that the field is very strong close to the poles. And of course, as we go farther away, the crowd decreases because the field becomes weaker. And the reason we get this pattern is because when you put this piece of iron close to a magnet, it automatically gets magnetized and starts behaving like a tiny compass. And as a result, it gives out this pattern. And another important property is that these field lines will never ever intersect. Now what I mean is, imagine we brought in another magnet into the picture. Then we might think at first that the field lines of this magnet will intersect with the field lines of this magnet. But that won't happen. This will not be the picture of the magnetic field lines due to two magnets. And the reason for that is because at the point of intersection, if we were to keep a magnetic compass or a magnetic needle, then this field line will make it point in this direction. But this field line will make it point in this direction. And a magnetic needle cannot point in two directions at the same time. That doesn't make any physical sense. And it's for that reason, field lines will never ever intersect. In fact, what will happen over here is that these field lines will now change. It'll become complicated, but they will change in such a way that they will never ever intersect. So in short, today we represent the magnetic field by drawing imaginary lines called the magnetic field lines. These field lines tell us in what direction the north pole of a tiny magnet points. So this line tells us the north pole of a tiny magnet kept here points this way. This field line tells us the north pole of a tiny magnet will point this way, and so on. And these field lines always form closed loops. Wherever the field lines are closer, the field is stronger, and they will never ever intersect.